In the description to this video, I'm going to put a link to a video I made demonstrating a curious phenomenon that you could do at home. I took a battery and I connected it up electrically to a little loop of wire. So a little loop that when connected to the battery, of course, it causes the current to flow through this little loop of wire and around it, around the wire. Now, what was interesting was when I put that little wire in the presence of a permanent magnet, because the magnetic field from that permanent magnet caused the wire with the current flowing through it to twist and turn. It generated a torque on that little loop. In this video, I want to explain the physics behind that phenomenon and also introduce you to the idea that motivates motors in our everyday life. In the video that I showed, it had a circular loop. For the simplicity of the mathematics, I'm going to stick with a rectangular loop, but the results that we get at the end will be very general and will apply to any shape of loop. So you can see here what I've got showing you is a little piece of wire that's been bent into a rectangle with the length of one side being L and the width being W. If I were to connect this to a potential, so that the leads were at different potentials, then we would get current flowing through the loop, possibly, for example, in the direction shown, where on one side we have the current going down towards the bottom of your screen, and as it comes across, then the other part of the loop is going to come to the left side of your screen, and then in the other part of the loop is going to go towards the top of the screen and come out. Okay. So it comes into the loop, goes around, and comes out. That's not that interesting. What's interesting is, of course, what happens when we put this loop in the presence of an external field. So for, again, the simplicity of the mathematics, I'm going to use a uniform magnetic field that is pointing from the left-hand side of your screen to the right-hand side of your screen. So I've got the current in this loop, and now I've got an external field. And we can calculate what the magnitude of the force on each piece of this current is by simply using the idea that some magnetic field will exert a force on a current. In fact, I can use this equation that if I take my current times the length of that piece of current crossed with the magnetic field, I will get the force. And if I looked at this cross product, what's interesting is that if my current points in the direction of my magnetic field, then the force on this piece of my current is 0. And if I look at this portion where the current is opposite the direction of the field, anti-parallel to the field, then once again, the force on this portion of my loop is 0. So the only part of the wire loop that contributes any force are this right-hand side and the left-hand side of my wire loop. So we're going to pay particular attention to those parts. What's also interesting is if you look at that, the current always points either down towards the bottom of your screen or up towards the top of your screen, whereas the magnetic field always points from left to right. So that at all times with this loop, the angle between the current and the magnetic field is 90 degrees. So this angle is always going to be 90 degrees, and the sine of 90 is 1. So that no matter what my orientation of my loop is, the contribution from either side will always be the same. It will not change no matter the orientation of my loop as far as turning it or twisting it goes. Now, we of course need to know, we need to use the external field. It's interesting if you look at the field generated by the the wire itself, if I were to look, for example, end on, so if I were going this way, looking from the bottom up towards the top of the screen, I would be able to see on the left-hand side, whereas my current was going up towards the top of the screen, if I look at it from the bottom, that would look like it's going now into the screen. And on the right-hand side, where it was coming towards the bottom, from the top to the bottom, now if I look at it from the bottom, it's going to look like it's coming towards me, coming out of the screen. And so I've just reoriented myself just so we can talk about what's going on. This is really a three-dimensional problem, and it's going to be a little bit hard if we limit ourselves to just looking at on a two-dimensional plane. Okay, so if I look at the end-on view, the field from the wire loop itself, from the current in the wire, would look something like this. Not quite circles, because in the middle region of between my loops, each side of the wire is going to contribute magnetic field pointing in the same direction, and so we're going to have a strengthening of the field. So my field lines should be closer together in the middle. On the outside portion of on the outside my loop portion, then each side of my loop is actually going to contribute magnetic field in the opposite direction. We're going to get a weakening of the field in that region, and so my magnetic field lines should end up spreading out. And so we don't quite get circles, we get sort of squished circles. But one point I want to make is that if you notice right in the center, the magnetic field is pointing towards the bottom of the screen for the orientation of current that we have. Okay, and I'm going to come back to this, but the magnetic field in the center of the loop, right in the center, is pointing towards the bottom of the screen. But of course, we don't care about the field from the loop itself. That's not what generates the force and is not what eventually twists this wire around. We want to know about what this current does in the presence of the external field. So we need to think about it in these terms and ignore that other field, the field that's coming from the loop itself. If we look at this and we look at our current, we can actually use a right-hand rule to find the direction of the force on each side of our loop. For the side to your left that has the current going into the screen, if I were to use my right-hand rule, I would find that my force points towards the bottom of the screen, and where it's coming out of the screen, I get exactly the opposite. So the direction of my force on each side of my wire, as given by my right-hand rule, will point in opposite directions. And the magnitude we've already been able to calculate. But you can see now where the origin of the twisting comes from. On one side of my loop it's being pulled up, on the other side of my loop it's being pushed down, and it seems to then sort of rotate about some point in the center. And that would be some axis of rotation that we would get for this loop of wire. Now, if there's a twisting or a turning, we can actually calculate what the torque contribution from each of these forces are to the twist of this wire. We'd have to choose an axis and then calculate the torque just by using the distance from that axis, or the displacement from that axis crossed with the force. That would give us our torque. And so if we choose an axis in the center, then the distance, the magnitude of this distance, would be just 1/2 the width of my wire loop here. That would be the distance from my axis to where my force is being exerted. To calculate the torque, my net torque on the loop itself is going to be the contribution from both halves of my wire, the right hand and the left hand side. And I can calculate what that is. You'll notice that they both have the same magnitude, and they are both trying to twist the wire in the same direction. As we look on this, this would be in the counterclockwise direction. So they both have the same magnitude and the same direction, so they will both contribute the same way. And then we can get the magnitude of our torque just by calculating the torque from 1 and multiplying it by 2. Now, in this orientation, the angle between my distance and my force is all set up to be 90 degrees. And as said before, the sine of 90 is going to be 1. So now we can just put in our magnitudes, the magnitude of our distance and the magnitude of our force. And what we find is that then the net torque on this wire is going to be the current in the wire times the length of the wire times the width of our rectangle, the length of the rectangle times the width of the rectangle, times the magnitude of our external field. Well, length times width, that's going to give us an area, specifically the area of this rectangle, this region in here, this area here. So we can actually generalize this to systems that aren't rectangular by simply saying, well, what if we just took the area? And believe it or not, this is a general result. If I take the current in my wire loop times the area of that loop times the magnitude of the magnetic field, I will get the torque. But be careful, that is the torque for this specific orientation of my loop in my magnetic field. So that begs the question, what happens if we have a different orientation? So let's look at an evolution of this loop as it turns. Of course, we started out with the orientation we just solved for. We found that the torque in this orientation is just the current in my loop times the area of my loop times the magnitude of the magnetic field. If we begin to turn this, we're going to have a change in the orientation of our force relative to this distance vector from our axis of rotation. We're now going to have an angle, whereas before our angle between the distance vector and our force vector was 90 degrees, so that the sine argument in our torque was 1, and we got some maximum torque. Now instead, our argument is less than 90 degrees, and that comes about because part of our force is no longer pointing perpendicular to this distance from our axis vector. Part of our force is still twisting the wire, twisting the loop around, but another part of our force is simply trying to pull the wires apart. And so only a portion of our force is contributing to the torque, and therefore our torque will be smaller. And if we keep going, we'll eventually get to a point where the loop ends up being, the plane of the loop, I should say, ends up being entirely perpendicular to the magnetic field, so that our distance vector from the axis of rotation and our force vector end up pointing in the same direction. And in this case, then the angle between those two is 0. So the sine argument is the sine of 0, which ends up being 0, and my torque is at a minimum now. I have a 0. I should say my torque is a 0 now. I have 0 torque. Okay. So we have the orientation that we can see how our torque actually depends on the orientation of our loop. It turns out that dealing with the force and the distance vector and the sine of the angle becomes a little bit cumbersome because we have two forces that we have to deal with. So traditionally, we typically define a direction for our loops, a direction vector that tells us the orientation of our loop. And we choose this vector by saying, look, if I had the plane of the loop, so if I took my loop and I dipped it in soap, it would create a little film across, filling up the space. Then this creates the plane of the loop. If I were to choose one, I have some choices. I could choose to designate the plane of the loop. That's typically not what people do. They typically choose something that is normal to that plane, which we call the normal vector. We have two choices we could choose. We could choose up or we could choose down. Remember how I said the magnetic field for this orientation of my current always points downwards in the middle? So typically, the convention is to choose that orientation. And we call that the normal vector. It's designated by a little n hat. And just to remind you, any vector hat, that little hat notation tells you that it has a size of 1. So that this is it really is just telling me what the direction is. If I multiplied this little n vector by my area, then I get a vector that has the magnitude of the area, but tells me the direction is in this normal vector direction. Okay. And now look what we've done. If we were to compare the direction or the angle between the normal vector and our magnetic field here, you would see that that's 90 degrees, which was the same as the angle between our distance vector and the direction of our force vector. If we were to look at this right-hand picture where we were, the plane of our loop was entirely perpendicular to the field, then if we look at the normal vector ends up pointing in the same direction as the field. And so the angle between my normal vector and the magnetic field also ends up being 0. In fact, no matter what orientation you have, it turns out that if I use this normal vector, the angle between the normal vector and the magnetic field is exactly going to be the same as the angle between my distance from my rotation axis, that vector, and the force vector that's doing the twisting. So with this, we can actually reduce the complexity. We don't have to worry about the force itself. We can simply take the magnetic field and the orientation of my loop and calculate the torque from that directly. And what we get when we put this together is, you can see we have the maximum, but it's modified by the sine of the angle between this normal vector and my magnetic field vector. By the way, if you have, we've done this for one loop. If I have more than one loop, say I have 10 loops, well, assuming they all have the current all moving in the same direction around the loop, then their effects will just add, and I can simply multiply my effect by 10. If I had 20 loops, I'd multiply by 20. And so you can see that we can find the torque from any number of wire loops or coil loops in a coil by simply multiplying by the number of loops in that coil. So we've been able to find now the torque on a current loop. And I want to remind you that even though we used a rectangular current loop, this result is general, that the torque on my loop depends on the number of windings in my loop, the current going through that coil, the area surrounded by those windings, and the magnitude of my magnetic field. And then we have to pay attention to orientation. And so we've defined this normal vector, and we look at the angle between the normal vector and my magnetic field direction. And the sine of that angle gives me this scaling factor so that we can calculate our torque. Now, typically you might see this if you're familiar with vector products, or if you've learned about the cross product, you'll see it written like this, where it's the current times the area times this normal vector crossed into the magnetic field vector. Sometimes people don't write the area or the normal vector. Instead, they'll write the area vector. They'll write the area vector instead, but you can see that the area vector is just going to be the area times this normal vector. So it's just a matter of notational differences here.